Okay, good morning, everyone. Let's get started. First of all, we have released homework 1 this morning, which is about decision trees. The homework 1 will ask you to show your understanding about decision tree learning algorithm and implement those decision tree algorithm ID3, which we're going to talk about throughout this class. So please start after this class. Look at homework 1 and think about it. You should be able to finish most of the problems after taking today's lecture. So do not hesitate. Please start working on it right now. Don't try to finish at the end of that last day. Okay, so today we're going to talk about how to learn decision trees, right? Namely, how we implement a machine learning algorithm which automatically construct the decision tree from some training data set, right? So in the last lecture, we talked about the definition of decision tree, right? So could anyone recall or summarize what's the decision tree? Any thought? There's no need to be shy. What is decision tree? Yes, exactly, right? So I want to add a little bit more details, right? Decision tree is a hierarchical structure that summarize the data, right? So you can view like each node in the tree represents a particular set of the data examples, right? The root node, the global root node will correspond to the whole data set. And then each intermediate nodes will represent a subset of examples, right? And the leaf node represents Urally represents a subset of examples which cannot be further partitioned. In most cases, it means all the labels in this subset are the same, right? That's the tree leaf node, right? And how do we construct the tree? Through our manual experience. We know that we can pick up, every time we can pick up an attribute, right? Remember the set of colored sheets, right? In our example, we first pick up the color, right? And then according to which particular attribute value those examples take, we can grow several branches, right? Each branch corresponds to the set of examples where that attribute takes a particular value, right? Like red, green, blue, right? And then when we arrive at the intermediate node, that means a subset of examples, we can pick up another attribute to do the further split. And again, the branches represent different possible values that attribute can take. Right? We just keep doing that until we find every subset of the examples has the same label. So we can stop growing the tree. We can just create a leaf node and assign the label to the leaf node, right? That's the basic definition of the decision trees. And I highly recommend you guys to manually construct such a tree, say following examples in our class by yourself to gain some kind of experience of that. Because today we're going to talk about how do we develop an algorithm to automatically construct such a tree, right? So we call this algorithm ID3 algorithm. It was invented about 40 years ago, but it's very, very classical and very popular. You will see that this ID3 algorithm essentially is a greedy heuristics that tries to build up a tree to be as small as possible, right? We briefly mentioned the motivation in the last lecture because we want to follow the so-called Occam's razor principle. That means I want my model to be as small as possible to fit the data. And then to find a globally minimum tree size, it will be NP hard. It's so hard. So we resort to a greedy approach. right? Which does not guarantee global minimum, but in practice, it always gives you a pretty small tree, right? That's how this ID3 algorithm is motivated. So here's some like sharing of history of decision tree research. It's just want to expand our historical knowledge. So it's a long history. So in 60s of last century, psychologists were trying to use some full search decision trees to model human concept learning. So you can see that it directly comes from observation of human learning behaviors. Then in late 70s of last century, Quinlan, he's the pioneer of artificial intelligence and machine learning. He developed this ID3 algorithm using information gain heuristics to learn the expert system from examples. By the way, in 1980s or late 1970s, expert system is kind of like the buzzword, like artificial intelligence or machine learning nowadays, right? So at that time, like expert system is the hottest area. So they call it expert system, but essentially the same, nothing different with learning system or artificial intelligence system. Like people always use like different words to represent a new trend, although the essence never changed. And then and later, three research scientists from IBM, this is from statistics, they developed the so-called CART algorithm. So we can view it as some kind of variants of ID3 algorithm. Their CART algorithm supports both classification and regression, right? And then in 1980s, there are a variety of improvements about decision trees, which we're going to talk about later after we introduce ID3 algorithm. We just talk about how do we cope with noise, how do we deal with continuous attributes. So we actually discussed about it in the last lecture, right? We can do the partition, we can do the binning, right? That's those methods were all proposed in the 1980s. How do we handle missing data, right? So we're going to discuss after we talk about ID3, right? And in 1990, Quinlan proposed an updated algorithm called C4.5. So this is the most widely used decision tree algorithm nowadays. And a more advanced version called C5.0, unfortunately, is commercial algorithm. You can now use it privately. You have to buy their software, something like that. So when I was a master student, we got some data mining course and asked us to try this algorithms. We got some access to a business intelligence software which implements the so-called C5.0. It's a surprisingly working well. And then later, based on decision tree, several ensemble learning algorithms were proposed for boosting and bagging, and it kind of like dramatically promotes the performance of decision tree algorithm, which is also the topic we're going to discuss after decision trees. So this is just a brief history to give you a sense how this line of research was developed. And honestly, nowadays, like even in many areas like financial control, like if you want to do some mortgage, right? You want to make a loan, I mean, not only for your real estate, but perhaps also for you're making some small companies, right? Their own personal loans, right? Like in bank system, like they use random forest a lot, or boosting trees a lot to predict whether you are able to to return those debt, right? To pay for this debt, or it's just someone who doesn't have like good financial status, they have like higher risk. Like they use this type of techniques to make the prediction. And also in medical study, like random forest decision trees and boosting trees are extremely popular, much more popular than artificial neural networks. And later we'll talk about why, because of the interpretability. Those are very, very important because they're not like just looking at your black box neural networks prediction. They're gonna give you $1 million. That's not like that, right? They need to know why the system or the machine learning algorithm tells that, okay, you are a reliable client or not. Okay, so to explain this ID3 algorithm, right? We want to be concrete, right? We don't want to be very abstractive. So we're gonna use one particular example to illustrate how this algorithm works. Right? So this example is to build a binary classifier according to the weather conditions decides whether I should play tennis outside or not. Okay. So we're going to use 4 features to represent the weather conditions. Okay. Outlook, temperature, humidity, and wind. Okay. So outlook, we got 3 possible values. There's a sun, right? There's overcast, right? A cloud, or there's a rain. All those features are discrete features. Right? And temperature, we got 3 possible temperature values: hot, mild, and cool. And humidity, right? We got 3 possible levels: high humidity, normal humidity, and low humidity. Right? And wind, we got 2 levels: strong wind and weak wind. Right? And labels, this is a binary classification task. So we got positive label, meaning that I'm gonna play tennis, right? A negative label, I stay at home. Everyone's clear about this setting? Okay. So to build a classifier, I collected the data from my past 2 weeks activities and decisions, right? So you can see that there are 14 pieces of examples, right? 1, 2, 3, until 14 here, right? And each line represents 1 piece of data, which give the values of the 4 features and my decision to stay at home or play tennis outside at that day. Okay? So here for simplicity, we use the capital first letter to represent, the feature name and feature value. And so outlook O, temperature T, humidity H, wind W, right? Their value, sunny, S, overcast O, raining R, right? Hot H, mild M, cool C, high H, normal N, low L, strong wind S, weak wind W. Right? That's that's what we say from the table, right? And here we mark the negative examples as red and positive example as positive, just to differentiate, 2 sets of examples. Is everyone clear about this data set? Observations. Those are data, right? Like you just record in the past 2 weeks, every day, what's the outlook, what's the temperature, humidity, wind, and whether you played outside or not. Right? You just accumulated your observations throughout like 14 days. You use that as your training set. You want to train a decision tree classifier so that, okay, for example, today I got a new set of features, right? And I'm gonna use my decision tree to decide whether I will play tennis outside or not. Yeah, that's possible. Another question? Okay, great. So if you use ID3 algorithm, right, run on this data set, right, it will recursively build decision tree from top-down fashion. That's what this tree will look like. Okay. So we can see that our ID3 algorithm first pick up the outlook feature to split data set. So we know that outlook feature can take three possible values, right? Sunny, overcast, and rain, right? Which gives us three subsets, right? And for each subset, it will recursively pick up a remaining attribute to the further partition, right? So for the sunny subset, it picks up humidity, and then do the further partition and end up with two leaf nodes, right? For the overcast, you see that it will directly give you the leaf node. And for the rain examples, it will pick up one attribute as the splitting attribute. It ends up with two leaf nodes, right? But how the algorithm fulfills this, right? So as we mentioned, right? So ID3 algorithm essentially is a recursive algorithm. So recursive algorithm means that it will repeatedly call itself to create new nodes and branches and expand the tree. Okay? That's the idea, right? So the input to this ID3 algorithm consists of three variables, right? The first one is the set of examples. Okay? So the set of examples, you can imagine at the beginning, it will be the entire data set, right? But remember, this is a recursive algorithm. So that means, okay, when it partitions the data into a list of subsets, right? For each subset, it might call ID3 again to do the further partition. So S actually represents a subset of the examples corresponding to the current node, right? And label are the labels, right? The target attributes associated with each example in S. The attributes is a set of available attributes from which you can pick up one to split on the data set. Does it make sense? So now imagine that you, as the algorithm developer, you want to design such a recursive algorithm, meaning that, okay, at the beginning, I'm calling my ID3 algorithm to split the whole data set into several small subsets. That means I create a root node, I create several branches, right? And then I'm gonna recursively call ID3 over each subset and to do the further partitioning, right? Until the leaf nodes, we should stop on some leaf nodes. Right? So if you want to design a recursive algorithm, what's the first thing you need to consider? Excuse me? Yes, the base case. That's very good. Last year I asked this like the whole class silent for 1 minute, right? And I mean, I just want to encourage, is there anyone else who can? What? My question is that if you want to design a recursive algorithm, what's the first thing you need to consider? You need to be concerned. Yes, stopping condition. Okay. Yeah, that's very good. So looks like everyone has a very good foundation for algorithm design and data structure. Okay, so if you haven't heard of recursive programming or don't have too much sense about algorithm design, that's fine. Right? But I want to tell you that if you want to design a recursive algorithm, the very important thing, the first priority is that you need to consider when you should stop recursion. Right? This is called the base case or stopping condition. Right? Why? Because if you don't specify appropriate stopping conditions, it will just call itself to expand the tree, right? And in computer science, people will know that like recursion is implemented by stacking, right? Every time it calls itself, it's gonna increase the stack pointer, right? If it keep calling itself, it's gonna make your stack overflow, and your algorithm will crash. And be careful. If you don't pay attention to this and implement this algorithm, if you see your algorithm just run forever, and then your whole system seems dead, it's very probably that your algorithm have eaten out all the stack memory and make your system crash. Okay, so now what is the base case, or what is the stopping condition? In other words, when should we stop growing the tree, stop partitioning S? Yes, example. Yes, excellent. Yeah, I didn't thought that you can give like full stopping conditions, right? Yeah. So when we did this manual construction, when did we stop growing the tree? We found out, okay, the current subset, they're uniquely labeled, right? The label is now mixed. So that means it's not useful, it's not meaningless to further partition that data set, right? So we stop growing the tree. That's one condition, right? But there is another condition. I think someone raised the question, right? So what if your attributes have been exhausted, right? Even you still have mixed labels, you don't have any available attributes. Your attribute set is empty. Then at that time you have to stop, right? Because you don't have anything to help you for the split data. So that's when should we should stop, right? We should create a leaf node, we just return. So let us look at the algorithm step to ensure everyone is clear about that, right? So whenever we call this ID3 algorithm, right, we should check if all the examples in S have the same label. If all the examples in S have the same label, that means, okay, there's no need to further partition S, right? We should create a leaf node to represent S and use that label as label for the leaf node, right? And there is a second condition that we have to stop as well. That is, if the attributes are empty, right? Then we cannot partition the data. Even if we want, we cannot, right? We don't have any attribute to further partition data. So we have to create a leaf node as well. And in this case, we're going to pick up the most common label as label for the leaf node. These are the base case or stopping conditions. Any questions so far? That's a very good question. So in this ID3 algorithm, you just use most common labels in S. So that's the local, right? But I'm not saying like you must absolutely follow this, right? You can use your favorite heuristics to assign it. For example, if you believe that, okay, I should use globally most common label, say throughout the whole data set, that's fine. Other question?
Say if attributes are empty, is that meaning that there are iterative group or
I'm not saying the example don't have any attributes. The example might have a list of attributes, but it's possible that even you use every attribute, even after you have used every attribute to split data set, then the remaining subset is still not purely labeled. That is possible, right? Yeah. I'm talking about that case. In that case, you have to stop as well, right? Because you don't have any additional attributes to help you arrive at the ideal case, right? Any other question? Okay, great. So your implementation, be sure to implement this first, right? To make sure that, okay, you consider the two cases. Otherwise, it is possible that your algorithm will show up working abnormally, right? Okay, so if it's not a stopping case, meaning that we have yet arrived at the leaf nodes, right? So we can do something. So first, we create a root node for the tree. So here, root node means some root node of the current subtree, right? So at the beginning, that root node may represent the whole tree, right? But when a recursive call this algorithm, it just represents some root node of the subtree, which we're gonna growing, right? And then from the attribute list, right? From here, right? This is a set of attributes, and now it is non-empty, right? We're gonna pick up an attribute from that list to best split the data set S, right? So someone may ask, like, what do you mean by best splitting, right? Let us hold off this question, right? Let's try to first capture the whole algorithm procedure, and then we're going to talk about the details about this, right? So suppose you got some mechanism to pick up the best attribute to split on the data set S, right? So, and then we're gonna enumerate every possible value A can take, right? For every possible value V, we're gonna grow a new branch tree, which associates with a testing condition that A equals to B. Meaning that, okay, if I want to test, I need, if I want to go through that branch, the corresponding test example must satisfy that its A attribute takes the value V. Okay. And then we denote by SV be the subset of examples in S whose attribute A takes value V. Right. If SV is empty, yes, we just mentioned, let us hold off this question. We're going to discuss about it later. So now here comes some subtle thing, right? If SV is empty, what shall we do? Any thought? It's possible that SV could be empty, right? Some attribute values, some attribute might take 3 possible values. Unfortunately, in all the examples in the S, right, in current subset S, they might just take 2 values, right? There could be some value where no example in S take that value, right? That means the corresponding SV will be empty. What if empty SV is empty? Yes, yes, yeah, we mentioned that, right? So even SV is empty, right? To ensure that the algorithm always gives some prediction, right? We're going to add a leaf node with the most common value of label in S. Right? But here, we choose to use most common label in S, right? But in practice, you can choose to use most common label in the whole data set or in some intermediate levels, whatever. And why is this? We can link it back to the color shapes example, right? And remember that when we just manually construct this decision tree, we start with color and then shape. When we use green, we look at the green shapes, right? We found that there are only rectangles and circles, right? There are no green triangles, right? So at that time, like someone has already asked, right? So what if I want to predict green triangle, right? So this tree is incomplete. It cannot give you any answer. However, if you use ID3 algorithm, we know that, okay, when we construct here, right? Even my branch, which corresponds to an empty, right? Triangle, green triangle part is empty, I'm gonna still create a leaf node, right? I'm gonna use the most common label in this corresponding subset associated with this node as my leaf node. It's labeled. That in this way, we can guarantee that no matter you got some attributes values missing in any subset, it always will give you some reasonable prediction. Right? Any question? Yeah, that's a very good question. So if your most common labels turn to be multiple, that means your labels are tied, right? You can pick up arbitrary. It's not necessarily you must specify some heuristics, right? If you want to specify some heuristics, like I prefer label A to label B when they have type, right? You can use that. But in our class and in our homework assignments, we don't have any specification on that. You can choose them randomly, or you can encode your own preference. Other question? You mean cross validation on what? Oh, yeah, you can use cross validation to do that, but people won't do that. Usually won't do that because it's a cross validation is kind of costly. Right? You can just specify some attribute on that, specify some label on that according to your own experience or preference. But it's totally up to you. If you want to use distinct cross validation to that, it's totally fine. Create a class. Oh, you can use whatever structure you want, but usually you can imagine that each tree node will have several attributes, right? You should have some pointer to the child node, right? You should have some attribute list, right? And then you're gonna, when you recursively call it, you can reference to the subset of examples, and also you can reference to its parent node. Right? So if you have any experience like data structure calls, you have implemented the tree traversal algorithm. We know how like pre-order, in-order, and post-order traversal, right? You just follow that framework. Right? Sorry, we're not going to talk about how do we implement the tree traversal in this class, but if you do have some concerns or problems, welcome to stop by the office. Any other question? Okay, so that's a very important detail here, right? So remember, implementation, you do need to check if every subset following a particular condition, right? Whether this attribute A takes particular value V, if it is empty, right? If it is empty, you still need to add a leaf node, assign the leaf node with the most common value of the label in S, right? If SV is not empty, what does it mean? It means that this data set can potentially be further partitioned, right? So that's where we're gonna call ID3 algorithm again here to further partition SV, right? So we're gonna call ID3 again, and now the input subset will be SV, right? Now the attributes, we should remove A. Why? Yeah, because A has already been used, right? SV, right? In SV, all the examples will have the same value in A, right? So you won't be able to use A to conduct any meaningful split, right? Because they all the examples whose value in A are the same, right? So I'm gonna kick out A in my attribute list, right? And labels are the labels of examples in SV. So in this way, I'm gonna recursive call ID3 again, and to further partition SV. Again, when we go back, right, they're gonna first check if all the examples in SV have the same label or your attributes have already been exhausted. If that's it, the SV will be represented by the leaf node, right? And assign the label. Otherwise, it's gonna go through this part to further partition them. Right? You do it again until all the leaf nodes are created. Right? Does it make sense? Right. So I want to conceptually draw some procedure, right, to give you a sense how this algorithm will run, right? So you can imagine at the beginning, I'm using rectangle to represent the current data set. This is a whole data set, right? So when you call ID3 with full data set and full attribute list, right? So you're gonna create a leaf node usually, right? It goes through this part, and then according to the attribute set, you can pick up most useful or optimal attribute to split data set. Like say you're gonna grow several branches, right? And each branch corresponds to a subset of examples, right? Okay. And then it will call ID3 recursively to further partition this subset. Then it either create leaf nodes. For example, here it creates leaf nodes because it satisfies the base case or stopping conditions, right? Or it found that it doesn't satisfy the base case, and then create a new leaf node and grow new branches, and then generate some subsets again, right? And for each subset, it's going to call ID3 algorithm again, right? Over each subset here, right? And then decide whether they satisfy the base case. If they are satisfied the base case, they might create a leaf node, right? If do not satisfy, they might further do some partition and go on, right? And then we then return back and go back to this third subset. They will do the same procedure to further partition and until all the base cases are satisfied and leaf nodes are constructed. Does it make sense? Right. That's how basically a recursive algorithm will execute. Right. Okay. So now let us return to one last question. Right? How do we pick up the attribute to split? Right? In our previous algorithm framework, we said that, okay, we have some mechanism to pick up the best attribute to split the current set S, right? But what do you mean by best split the data set? So here, our goal is to make the resulting decision tree to be as small as possible. Okay. Why should we choose this goal? Because it respects the so-called Occam's razor principle. Right? So what does Occam's razor principle mean? It means that, okay, for the same data set, right, you might have 10 models to explain the data set. In other words, you may have 10 models to very well match the data, well fit the data, right? Now, you want to pick up one of it. Which one would you like to pick? Yes, the one with the simplest. Like, why? This is just the philosophical principle. There's no rigorous mathematical proof, but many science, engineering practice are verified by this Occam's razor principle. Like many examples. Like for example, I mean, long time ago, people believed that Earth is the center of the universe, right? And they use that to build out a system theory to show to predict when eclipse will happen, all kinds of stuff. I can tell you that system works very well. It was developed by a ancient, I think it's Greek scientist. It's called Ptolemy, right? He used a set of techniques. It's called a bunch of circles, small circles, big circles, large circles, and the fairly complicated math computation to approximate the orbit of those kind of stuff and make prediction. Is working fairly well. But then later, another people proposed a theory said, okay, the sun should be the center, right? And all the other planets, including Earth, is running around the sun, right? And like people at the beginning doesn't believe it, right? But using sun as the center actually can largely reduce the complexity of theory. Even you can use even the accuracy is even slightly worse than Ptolemy's theory, but people finally eventually accept that. And of course, later when with the development of modern astronomy and people use telescope to look at those kind of things, people verify that okay, it's indeed like Earth is surrounding suns, right? And also, if you want to compute the orbit, you have to use Newton mechanism, right? You have to know the integration and Newton's laws, those kind of stuff is it's quite difficult to compute, right? But anyway, that's one example to showing that okay, a simpler model is always more favored, right? In the case that all those models have the same power to fit the data, to explain data. Right? So we're going to talk about that later, because from time to now, we'll see that how Occam's razor is reflected in every aspect of machine learning. Right? But now let us assume that, okay, our goal is to find the minimum decision tree consistent with data, right? However, if we want to find a global minimum decision tree, such a tree is very hard to find. The cost is very expensive. So it's going to be NP hard. Why? Because imagine that you have to enumerate all possible orders of attributes to split data, right? So if you have n, you have n attributes, then such orders will take factorial of n, right? That's very, very large search number, right? Even you use very smart pruning strategy, it will be very complex, right? So in practice, right, we want our decision tree learning to be very, very efficient, right? We don't want to get stuck in like such kind of global search. So we choose to some greedy heuristic approach. So what do you mean by greedy heuristic? The idea is as follows, right? I'm not gonna enumerate all possible permutation of these attributes to split. Instead, every time I'm gonna just select a feature to split data to make it as purely as possible based on the previous result. I pick up the attribute to find out the best attribute. That means, okay, using that attribute, the purity of labels across those subsets increases most. Okay? And then I'm going to fix that attribute A. Next, I'm going to pick up a second attribute, which by applying B, say B, right, over all the subsets generated by A, my purity, label purity improves most. So you can see that every time it tries to maximize locally, right? But imagine that because every step I'm trying to maximize the impurity improvement, right? And it won't take too much steps to stop growing the tree, right? Because every time I'm trying to make my labels of each subset to be as pure as possible, right? Now I can imagine that after only a few steps, I might make my every subset of examples to be unique label. So that's the idea. Question? That's a good question, because we need some like rigorous definition to measure the so-called purity. But you can imagine that, okay, if I got 100 examples in a subset, right? And if I got 90 examples positive and 10 examples negative, which is pure, then I got only 80 examples positive and 20 examples negative, right? And next, we're going to define how should we measure such kind of purity. The label is specified by you, right? For example, if I want to play tennis outside, right? This is the label, right? And attributes is also decided by you, right? I want to use 4 features. Right? This should be defined before we conduct such kind of learning. No, it's nothing about efficiency. It's about how you define a task, right? At the beginning, if you want to conduct supervised learning task, right, as we discussed in last class, right, you should specify what is label space, what is the instance space, right? Instance space consists of the feature representation of your instances, right? And of course, like, how do you choose those attributes? This is a big branch, right, of experience, right? It's very important actually in practice. But here, we're gonna focus on, okay, suppose you already have a list of features ready. You know the labels, you know the task, right? And how do we conduct learning procedure? Any other question? With respect to, yeah. Right now, I'm just talking about this line of sentence. Yeah, any question regarding understanding this line of sentence, right? This is talking about our greedy strategy, right? So everyone is good with that? Okay, so as some of you have pointed out, right? So I kind of understand, okay, it's reasonable to do this greedy heuristic. Every time I locally want to maximize the improvement of purity, right? Now that question will be, okay, how do we measure the purity, right? I need to rank the features. I need to rank those attributes, right? I need to rank what's the ability of each attribute to improve the purity, right? But first, I need to measure what do you mean by purity, right? I give some intuition. Right? Suppose I have 100 examples using attribute A. I split it. I got 2 subsets. Like now, like I got like say one subset like 90 positive and 10 negative, right? I suppose I use another attribute and split the subset. I still are like 100 examples, but only 80 positive, 20 negative, right? Of course, the first one should be more pure, right? So let us look at one concrete example, right? Suppose we got data with 2 balloon attributes, A and B, right? And we got 4 trunks of data examples, right? When A and B are both 0, we got them to be negative. We got 50 negative examples. And we got 50 negative examples with A0, B1, and 0 examples with A1, B0, and 100 positive examples with A and B both 1. So now the question is, which should be the first attribute we select? So let us try to look at, right? Let us look at what happens if we use A to split on the data set, and what happens if we use B to split on the data set, right? So if we use A to split on data set, right? We know that when A equals to, sorry, when A equals to 1, right? This actually corresponds to this one, right? So we got 100 positive example, and when A equals to 0, it corresponds to this subset. We got 100 negative examples. Seems very good, right? And each subset achieves a maximum purity. Right? Then let us look at what if we use B to split. Right? When B is 1, right? That means here and here. This one and this one. We got 150 examples in total, and definitely mixed. Right? because 100 are positive, 50 are negative, right? When B equals to 0, it's here and here, and this one is better. We have 50 examples in total, and they are all negative, right? But the problem is that for this subset, right, where B is 1, it is highly mixed, right? I got to use A to split again to ensure the further partitions are given uniquely labeled subsets, right? So now, which attribute should we choose? Definitely A, right? And because after using A to split data set, the purity of those subsets are much higher than the subsets generated by using B to split the data set, right? We're going to use machine to do that, right? Because we're developing machine learning algorithm, right? This should be automatically done by your algorithm, not by you. Any other question? I'm going to talk about how do we this, how we're going to do this automatically. Yeah, just one by one. Yeah, you see that doing this is very quick, very fast, right? But we need to first know how we do this, right? How do we measure the purity after you use each attribute to split on data sets, right? And then you're going to rank those attributes and pick up the best one, right? Any question regarding here? Okay, this one is a very simple and intuitive case, right? So what if in both cases you won't get unique labeled subsets? In every case, it's like no matter you use A and use B, you in both cases you get mixed labeled subsets, right? Then let us see how should we rank the purity. So here we're gonna just add 3 examples here. We put 3 inactive examples where A is 1 and B is 0. And in this case, let us try to compare attribute A and attribute B, right? If we use A to split the data set, right? When A equals to 1, right? Equals 1, we got this one, right? So now we have 103 examples, and they are not uniquely labeled anymore, right? Because 100 are positive and 3 are negative. And when A equals to 0, this subset still corresponds to a unique labeled subset, right? As a comparison, like if we use B to split the data set, what will happen, right? When B equals to 1, right? It should be here and here, right? We got 150 examples where 100 are positive and 50 are negative, right? When B equals to 0, right? Here and here, we got 53 examples, all of which are negative, right? So now we can see that, okay, seems like using, no matter using A or using B, like it do not end up with like purely labeled subsets, right? But now, if you're asked to rank A and B, which one would you think is better? B, why is B? I mean, just give me a guess, right? Any guess or any thought? Still A, why? Yes, right? So we can see that although like using A and using B, like you end up with like the first subset or not are mixed, right? But the purity of the labels in A are still much higher, like than purity of labels in here, right? Which arise from using B, right? So you can see that, okay, 103 examples, 100 positive, only 3 are negative, right? Only a small portion are negative. But here, look, it's a 2/3 positive, 1/3 negative, right? It's highly mixed. So that means I'm gonna still prefer using attribute A, right? So now comes into the question, right? How can we invent a computational metric to measure the purity improvement after I using every attribute A to split the data set, right? So if I can invent such a computational metric so that I can compute for every attribute, what's their purity improvement to splitting the data set, right? And then I can rank them. That's the idea. Does it make sense? Okay. So we're gonna introduce the most popular heuristics, right? It's called information gain, right? But I have to mention that there could be a variety of metrics, right? Here I just introduced the most popular one, is called information gain. And later we'll talk about some variants. It's called Gini index. It's called majority gain. But what is the information gain, right? So to understand what is information gain, we need to do a brief review about the concept called entropy. How many of you have heard of entropy? Okay, great. So entropy is a basic concept in information theory. It's a very widely used concept. So basically, you can view entropy measures the uncertainty about some random variables. For example, the labels for a set of examples, right? Because you don't know exactly the relationship between your input and output, so you can view those labels as random, right? The entropy represents how uncertain I feel about the labels for this set of examples. Okay? How do we compute the entropy? If your labels are binary, right, I'm gonna compute the proportion of positive, we denote by P plus, right? Proportion negatives, we denote by P negative, right? Suppose you got 100 examples, 80 positive, 20 negative, then proportional, then P positive is 80 over 20. 80 over 100 is 0.8, right? And P negative is just 0.2. And then the entropy is defined as the negative P positive logarithm P positive subtracted P negative logarithm P negative. I don't ask me why it's defined like that. It actually has a very strong reason. It's out of the scope of this class. And we can extend the entropy for the binary variables or binary labels to multi-class labels. So suppose you got k possible labels with probabilities P1 to Pk. Then the entropy is given by the summation of negative Pi logarithm Pi, where I starting from 1 to big K. That's the definition. So what does entropy reflect, right? Actually, it's highly consistent with our intuition about uncertainty. Why? If all the examples belong to the same label, then the entropy is 0. It's very intuitive, right? If all the examples have the same label, no matter it's positive or negative, that means, okay, I don't have any uncertainty about the labels, right? I know it must be positive or negative, right? So my uncertainty is 0. And we'll calculate that one, it gives you 0. Right? So someone may ask, okay, what if I got 0 times log 0, right? So this can be sidestepped by view as a limit. Right? It's just some mathematical detail. You can just ignore it. Okay. On the other hand, right, if P positive and P negative is 0.5, then entropy reaches the maximum is 1. It is also very intuitive, right? Why? Because if the probability that the label is positive is the same as probability that the label is negative, that means my uncertainty about those labels are maximum, right? I really don't know which label it could be, right? It could be positive, could be negative, they have an equal chance, right? So I reach a maximum entropy. Does it make sense? Right. So here's some example showing that, okay, for different P positive, P negative, so what is the entropy, right? So those x-axis shows P positive, P negative, right? And then this blue bar shows like what is entropy. So you can see that when P positive, P negative are equal, your entropy goes to the max, becomes the max, right? And the more unbalanced about this P positive and P negative, the smaller the entropy, meaning that the less uncertain you are about those labels. Does it make sense? Right. So such observation applies to multi-class labels. Right? Suppose you got k labels, right? K possible labels, right? You calculate entropy in this way, right? So if you look at how entropy varies along different values of P1 to Pk, right? You see that when all P1 to Pk are the same, you got the highest entropy. That is uniform distribution, right? And when you have some one Pk dominates all the others, your entropy is very small. This is very reasonable, right? If you know the label to be class 1 is 90% chance, right? It is much certain that, okay, you don't know, every label has the equal chance, right? So now, so first I would like to make sure that everyone feels comfortable with this definition of constant entropy. Reasonable, right? So now let us build the link, right? The link is here, right? Entropy measures the uncertainty, right? High entropy means high uncertainty. High uncertainty implies low purity, right? So as we mentioned, right? If your proportion of positive examples, negative examples kind of the same, the purity is very bad, right? It's highly mixed. That means you have the very high uncertainty about the labels in your data, right? That means you have high entropy. Does it make sense? Right? On the contrary, low entropy means little uncertainty. Right? Little uncertainty means that the labels in your data set is quite pure, right? Maybe 99% of the labels are positive or negative, right? Only a small portion negative. So it means you are pretty certain about the labels in your data set. That means the purity of your labels are high. Does it make sense? So you can see that the purity and entropy looks like two sides of a coin, right? High entropy means low purity. Low entropy means high purity. Does it make sense? Okay. Then here comes come back to our question, right? We want some measurement which measures using a particular attribute what is the improvement of the label purity, right? So you can see that the increase of the improvement of purity can be represented by the decrease of the entropy. Okay? So now I find a way to measure how purity changes after we use an attribute to split on data set. Does it make sense? Okay. Any question? Like if you feel like, okay, I kind of like hard to hit the point, it doesn't matter. There's some kind of link here. You just read these slides 2 times or 3 times, you get it. Okay. But here, the idea is simple because entropy comes from the concept of information theory. It measures uncertainty, and uncertainty is another side of describes the purity, right? High uncertainty means low purity, and low uncertainty means high purity. So I'm going to use the decrease of entropy to represent the increase of the purity. Okay, so here we come to so-called information gain definition. The information gain is defined over a data set S and a particular attribute A. Right? And to calculate that, we're going to first use A to split S. Right? We know that we're going to have a list of subsets, right? Then the information gain is computed by first the entropy of the entire data set S. Right? Then we subtract it by a weighted summation of the entropy of each subset after use A to split S. Right? And here weights is just the proportion of the size of each subset with respect to the whole size of the whole data set. So you can view it as a weighted average of the entropy of the subsets using A or generated by A. So now from the definition, we can see that this is essentially the reduction of the entropy, right? Before we split S with A, we got an entropy of the whole data set, right? After we use A to split on S, we got a list of subsets, right? Then we just compute the entropy of each subset, and we do a weighted average over that. Then we look at the difference between the entropy of the whole set and the weighted average of each subset. Does it make sense? Any question regarding the definition? Okay. Yeah, this is very important. That's why, yeah, I want to, like, you can imagine like this is your whole S, right? You got some entropy over that. That's how we compute that, right? Then after using some attribute A, you're gonna split it into, say, 3 subsets, right? Each subset will have its own entropy. You just do a weighted average. The weight is proportional to the size of each subset. Now you just compute the difference between the entropy over the whole set and the average entropy over the subsets. It reflects what is the decrease or what is reduction of the entropy after you're using A to split S. As we just discussed, right? The reduction of the entropy measures the improvement of the label purity. Right? So the more reduction of the entropy implies the better improvement of the purity. Right? Then we can just rank the information gain of every attribute and pick the one who has the largest information gain. We use that as our best attribute. Does it make sense? Right? That's how it. No, entropy is always non-negative. And one interesting thing, like if you're interested, like please take a look at homework 1, right? There's one bonus question, asks you to show that information gain is always non-negative as well. Remember, this is a reduction of entropy, right? So always non-negative means that, okay, as long as you use some attribute to split on data set, your entropy will always decrease. That means your label purity is always will improve, right? Feel free to think about how to prove that. It'll definitely deepen your understanding of this. Any question regarding definition? Okay, looks like it's straightforward for everyone, right? Okay, so here I just want to mention that why should we consider weight? That's because we want to differentiate subsets of different sizes, right? The larger subset, of course, is more important. Like for example, you got one subset is 100, right? The other subset just 10. Of course, the larger subset, their label purity or their entropy is viewed as more important than the smaller subset. Okay. So now we want to use this example to show how we apply the information gain to rank those attributes, select them to construct our tree. Right? We'll go back to this data set, right? We got 14 examples, right? So at the beginning, we need to choose, right? From these 4 attributes, which one we should use, or which one we should will is best to split data set. How can we do that? I heard that, right? We're going to compute the information gain for each attribute and pick up the one who has the largest information gain, right? Because the largest information gain means that, okay, using that attribute to split on data set, you got the largest improvement of the best improvement of the label purity. Right? So let us compute, right? So first of all, we need to compute entropy of the entire data set, the entropy over these 14 examples, okay? And which is fairly straightforward. We just need to compute what is positive ratio and negative ratio, right? So positive ratio is just 9 over 14. You just count how many positive signs in the labels, right? Which is 9. And I got 5 negative labels, which are red, right? So, and then we just use the formula to compute the entropy of the whole data set, which is negative, positive ratio, logarithm, positive ratio, subtractive, negative, subtracted by a negative ratio, logarithm, negative ratio, which is 0.94. Next, we're going to take a look at after using each attribute to split on data sets, right? What is the entropy of each subset? What is their weighted average? And what is their information gain? Right? Let's just follow the definition of the information gain. Right? So first, if we use outlook, right? We know that outlook can take 3 possible values, right? Sunny, overcast, and raining, right? So we're going to look at each subset. Right? So for the sunny subset, which are marked by those rectangles, right? So we see that there are 5 sunny examples, right? All those 5 examples, we know that there are 2 here and here are positive, right? The remaining 3 are negative. So the positive ratio is 2 over 5. And negative ratio is 3 over 5. You just use the formula to compute the entropy, which is 0.971. Right? And similarly, if you take a look at overcast examples, right? Is here, 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 and here. Right? You see that all 4 examples are positive, so the entropy is simply 0. Right? And I mean, it's quite mechanical. You can compute what is the entropy for the raining examples, which contains here, 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 and here, right? All those 5 examples, right? We know 3 are positive and 2 are negative, so the entropy is 0.971. Right? Then we just need to compute the expected entropy. That is the weighted average of those entropy over the 3 subsets, right? So the first sunny subset, take 5 examples. So the weight is 5 over 14, right? Second subset, overcast examples, right? Take 4 examples. So weight is 4 over 14. The third one, 5 over 14, right? And just do the weighted summation, you get the expected entropy over those subsets is 0.694. Then your information gain, according to the definition, will be the entropy of the whole data set subtracted by the expected entropy over the subsets, which is 0.246. So now we get our information gain for the first attribute outlook, which is 0.246, right? You just follow exactly the same procedure to compute the information gain for humidity, which I'm not gonna show the details, but I highly recommend you guys to calculate, right? So we use humidity to split on data set. It'll give you 2 subsets. One is high humidity, one is normal humidity. This is their entropy, their expected entropy, and the information gain is 0.1515, right? Just to follow the computation, we got information gain for outlook, humidity, wind, temperature. So now, can you tell me which attribute should we use? Outlook, right? Outlook has the highest information gain, means that we believe using outlook to split the data set, the label purity will be mostly improved, right? So we split on outlook. That's where we finish the first step. Right? So you can see the finished first step. We pick an outlook, and according to the outlook, right, we generate 3 subsets, right? For sunny, for overcast, for rain. Right? And next, we're gonna call ID3 algorithm recursively to further partition on the 3 subset, right? So now I want to ask, let us look at the middle one. For the overcast, do we need to further compute the information gain? No, why? Yeah, because all the examples have the same label, right? Remember the base case in ID3, right? Before we consider splitting the data, right? We first check if all the examples have the same label. If they have the same label, that means, okay, we got the leaf node, right? We just stop there. We just create leaf node. We assign the label. Okay. Then we can take a look at the remaining 2 subsets, right? So for the sunny subset, right, we know that outlook value is sunny. That's why when we call ID3 again to partition this example, right, we're going to kick out outlook. Right? Because outlook has been used and all the examples take the same value. It's not meaningful to use it anymore, right? We'll look at the information gain for the remaining attributes, temperature, humidity, and wind, right? And then what you need to do is just, compute the information gain, splitting on this subset with temperature, humidity, and wind is here, here, and here. So according to the value, which one should we use? Humidity, right? Because humidity has the largest information gain. So I'm going to use humidity to further split on these 5 examples. Right? So it will end up with 2 subsets, and each subset is unique label. So we create leaf nodes on that, right? And similarly, and one more thing that's very important, right? So we found that in this subset, your humidity only contains 2 values, right? High and normal. But humidity can take 3 possible values. You got a low value. You don't have any example show up to have a humidity value to be low. And what should we do? We still need to create a branch, right? we should to create a leaf node, and then we use the majority label in this subset as the label for the leaf node, right? And the majority label here in this subset is no, right? That's why in our leaf node here, we assign label no. Right? Does it make sense? Okay, is everyone comfortable? Okay. And similarly, you can compute the information gain over this range subset, end up with one attribute. Given the highest information gain, use that to split, and you got two purely labeled subsets. So you finish the construction of the tree. That's the whole algorithm framework. Okay, thanks. Let us continue the discussion on Thursday.